In the previous module, we have already taken a look at the effects of omission of relevant variables and inclusion of irrelevant variables, and also discussed some tests for the same. These are part of a general type of errors called specification errors, which we will discuss through a broad outline in this module. So, specification errors can be of various types, namely omission of relevant variable, inclusion of irrelevant variable, incorrect functional form, error in measuring variables, incorrect specification of the disturbance term, and non-normality of the disturbance term u. We have already covered in the previous module the first two types, and we will take a look at a broad outline of the rest of the types of specification errors. So, we begin with incorrect functional form. Let us suppose we are considering the estimation of a cost function which should be of cubic type. So, we have a regression of y on xi, xi square and xi cube, that is a cubic cost function. This is the correctly specified model, whereas supposing that a person estimates a linear function which is an incorrectly specified model. You will have noticed that we had used a similar example when we discussed omission of relevant variables. The same example can be taken in the context of incorrect functional form. So, here the functional form of the model which is going to be fitted is incorrect because we have omitted x square and x3, x square and x cube. So, again this will give the same results as we had obtained when we had incorrectly specified the model by omitting these variables. And now we will discuss a test called regression specification error test. So, this test will help us to understand whether actually the functional form that has been taken is incorrect. So, let us look at the steps of this test. First, we fit the model I. That means incorrectly we fit the model, but then we know that from this model we will get estimated y. So, we will get y hat I from the incorrectly specified model. Now, next what we do is we regress yi on the variable x, that is beta 1 plus beta 2 xi, and for the omitted part we use the estimate that we have already obtained. So, the rest is beta 3 yi hat square plus beta 4 yi hat cube plus ui. So, that is the regression then that we run. So, then run the regression which is yi regressed on variable x, and for the incorrect specification part we take the estimated yi, the square of that and the cube of that. And now the test statistic that we use is given by r square new minus r square old divided by q all upon 1 minus r square new divided by n minus k. Let us explain what this means. So, this is the old one and this is the new one. This is the new one, that is the old one. So, this actually comes from our familiar concept of f is equal to restricted residual sum of squares minus unrestricted residual sum of squares divided by number of restrictions all upon unrestricted residual sum of squares divided by n minus k. So, it is very easy to understand. As you see, this model contains two more variables, yi hat square and yi hat cube, whereas this model does not contain these. So, this model, which is the incorrectly specified model, is the restricted model, and this is the unrestricted model, where both yi hat square and yi hat cube have been taken into account to test whether this model fitted is actually of the incorrect specification. Now, if you divide throughout by total sum of squares, then this will be 1 minus r square, 1 minus r square of the restricted model. This will be 1 minus r square of the unrestricted model or new model. So, because you have a minus sign, you have r square new. Because of the minus sign over here, 1 minus r square new. So, that will be r square new. And here you already have 1 minus r square old. So, that is minus of r square old, and 1 and minus 1 get cancelled. So, this divided by total sum of squares both in the numerator and denominator will fetch us this test statistic, which is nothing but f is equal to this with q and n minus k degrees of freedom. And then we know from our earlier modules how to use the test statistic to test H naught, that beta 3 and beta 4 are both equal to 0. So, this is one important test that we can carry out. Another test is called the Durbin-Watson test, has already been covered in an earlier module. I will just give the logic why we do this Durbin-Watson test here. So, because you have this incorrectly specified model as yi equal to alpha 1 plus alpha 2 xi plus vi, that means this vi actually incorporates effects of xi square and xi cube together with this ui. So, what I want to impress upon you is this vi actually is affected by three things. One is xi square, xi cube and ui. So, actually the disturbance term is only ui, but the fitted model incorrectly specified actually will lead to the effect that this apparent disturbance term will contain the effects of the actual disturbance term plus these two things, these two variables which are omitted due to incorrect functional form. So, therefore, covariance Vi Vj will not be equal to 0. So, that will give rise to serial correlation or auto correlation, which does not happen if the model is properly specified. So, because Vi and Vj will be correlated, they will be correlated because xi square and xi cube will be there both for the ith term and the jth term. So, this will lead to covariance between Vi and Vj. So, a good test to find out whether an error has been made due to incorrect specification is to go for the Durbin-Watson test, given by the test statistic d is approximately equal to 2 into 1 minus rho. This has already been covered in an earlier module, and we know that the Durbin-Watson test statistic can help us to detect first order autocorrelation, both positive and negative. So, if we obtain from the test the result that there is actually autocorrelation, then one reason for that could be an incorrectly specified functional form leading to this problem. Next, what we will take a look at is what happens if there are errors in measurement of variables. Viewers, now we take a look at error in measurement. So, y is regressed on x and there can be errors in measuring y as also in x. So, first we will take a look at the effects of error in measurement of y. So, we write the model as y star I is equal to alpha plus beta xi plus ui. So, y star is the value of y if it had been correctly measured. This is the correct measure of y, whereas what the researcher measures is yi equal to yi star plus vi. So, there is an error in measuring yi. The true measure is yi star and the measure that is obtained is yi star plus vi. So, when we incorporate this into the model or when we take account of this in the model, what we get is we are regressing actually yi on xi, because the researcher has data on y and x, but this y is not correctly measured, it is the correct measure plus some error. So, we will write therefore yi is equal to, instead of y star we write alpha plus beta xi plus ui, and then we also have to write plus vi. So, this is y star and this is vi. Therefore, the model actually becomes alpha plus beta xi plus ui plus vi. So, that is the model which is being run by the researcher, and therefore, beta hat, as we all know, is summation yi xi divide summation xi square. Now, we will see that this estimate is unbiased. So, that is equal to, instead of y, what we write is in deviation form. That means, instead of y we will write b small xi plus ui minus u bar plus vi minus v bar. That is y in deviation form, beta xi minus x bar small xi, ui minus u bar and vi minus v bar. This thing multiplied by xi multiplied by xi and the whole thing divided by summation xi square. That will again be equal to, if you see, u bar summation xi and v bar summation xi will be equal to 0, and beta is multiplied by xi and again multiplied by xi. So, this will be beta summation xi square plus summation ui xi plus summation vi xi all upon summation xi square. And therefore, viewers, when we take expectation of beta hat, what we obtain is beta in the first place plus, by the properties of the classical model, expectation ui xi is equal to 0 and expectation vi xi is also equal to 0, because this ui and vi, they follow the properties of the classical model. So, this is equal to beta. So, we get the nice result that although y may be incorrectly measured, the estimate is unbiased. What then is the problem? We will see that the variance will lead to a problem, variance will be larger. So, we continue over here and let us try and find out the variance of beta hat. So, from this model, the variance of beta hat, which is given by expectation of beta hat minus expectation beta hat squared, is obtained as expectation of beta hat minus beta squared, which is expectation of summation ui xi plus summation vi xi divided by summation xi square whole square. Please take a look. So, expectation of beta hat is beta. So, expectation of beta hat minus beta, expectation of beta hat minus beta whole square means beta hat minus beta, that is this term, summation ui xi plus summation vi xi divide xi square, the square of that. And therefore, variance of beta hat will be equal to, now let us take a look at the square of this term. So, in the denominator, or first let us write the expectation operator and then let us write the denominator. So, that will be xi square whole square. Now, here when we take the square of this, we will get like terms and unlike terms. So, you will get ui xi, like terms means ui square xi square, and unlike terms means ui uj xi xj. And because there is no serial correlation over here, the cross product's expectation will be equal to 0. So, we are only left with the paired terms. So, we are writing summation ui square xi square plus summation vi square xi square. Please note carefully that we have omitted the other terms not because they are 0, but because the expectation of those other terms are 0. We will have terms with ui uj xi xj and vi vj xi xj and also cross products between these, but those terms, when we take the expectation, those terms will be equal to 0. So, bottom line is you can write this as expectation of ui square xi square summation plus vi square xi square summation, and that will give us, if you take xi square common, summation xi square will be common, because expectation of ui square is equal to sigma square u and expectation of vi square is sigma square v divided by xi square whole square. I repeat, when you take expectation of this first term, then for each ui square you get sigma square u, for each vi square you get sigma square v, and therefore, you can take out sigma square u, sigma square v, and then you can have xi square whole square common, and that xi square summation common, that with the denominator, that is summation xi square whole square, gives this final result, which simplifies to sigma square u plus sigma square v divided by summation xi square. So, this has one constant. When you apply the expectation operator, it has one constant, summation xi square. This is another constant, summation xi square. So, summation xi square is common. Take the two constants and put them in a bracket, and xi square gets cancelled with xi square whole square. Now, if you take a look at the correct model, if you had actually been able to measure yi star without the error, then from here we would have obtained variance of beta hat would be equal to sigma square only divided by xi square. So, naturally you can see that this is sigma square u, because you have u here. So, naturally you can see the variance of the incorrectly specified model is larger than the variance of the correctly specified model. So, that is the problem that we have when we run into error of measurement of y. Now, when we have error of measurement of x, the problem is much more serious. Let us now take a look at what happens when we measure x incorrectly. So, the model has to be rewritten and we proceed as follows. Now, yi is correctly measured. So, yi is regressed on xi star. So, what we should regress yi on is xi star, but we have been able to measure only xi, which is equal to xi star plus wi. So, xi is the measure that we have, xi star is the measure that is the correct measure which we do not have. So, the observed measure is the correct measure plus error. Now, that means when we regress y on xi star, actually therefore, xi star is equal to xi minus wi, and when we incorporate this into the model, the result that we have is yi is equal to alpha plus beta times, instead of xi star we will write xi minus wi plus ui. So, that is equal to alpha plus beta xi plus ui minus beta wi, and this we can write as alpha plus beta xi plus zi. So, finally, the person running the model will run this particular regression where y is regressed on x and the residue z is ui minus beta wi, where wi is the error in measuring x. Now, the problem over here is one of the vital assumptions of the classical linear regression model is that the disturbance term should not be correlated with the regressor. So, covariance between the regressor and the disturbance term should be 0, but in this model the regressor is xi and the disturbance term is ui minus beta wi, but xi and wi are related, xi and wi are related. So, we run into a serious problem, that is covariance between zi and xi is no longer equal to 0. I repeat, zi, the disturbance term of the incorrect model, and xi, the regressor of the incorrect model, they now become correlated. Their covariance is no longer equal to 0. So, therefore, their correlation will also not be equal to 0. Why? Because the disturbance term in this incorrectly specified model contains an error in measuring x. So, that error is w, and naturally that error is associated with x. So, there is some association between x and z. More specifically, this covariance is equal to expectation of zi minus expectation zi times xi minus expectation xi. So, that is the covariance in the population, of course, and what is expectation of zi? That is expectation of ui minus beta wi, and by the classical property is expectation ui equal to 0, expectation wi equal to 0. So, this term will be equal to 0. So, we can write this as expectation of zi, and what about xi minus expectation of xi? So, xi is this, and what is expectation of xi? Expectation of xi star plus expectation of w, which is equal to 0. So, we have xi minus expectation of xi is xi star. So, this comes out as wi. So, this is wi, because expectation of xi is xi star. So, xi minus xi star is wi. So, that is this wi, and therefore, we have this result, expectation of zi is ui minus beta wi, that is multiplied with wi, and naturally you see there is a wi square term, there is a wi square term which is variance of wi. So, this will be equal to minus of beta sigma square w. U and w are uncorrelated, the first term is taken care of, but second term is minus beta wi square, and expectation of wi square, this is because since expectation of wi square is by definition equal to sigma square w. So, z and x, the disturbance term, random disturbance term and the regressor, they are correlated. So, the property, the fundamental assumption of classical linear regression model falls through. So, therefore, we will have biased and inconsistent estimate. Bias is all right, but oftentimes what happens is, in a finite sample, if you have a bias, then that bias comes down as the sample size increases. That also will not happen here, because this fundamental assumption of zero covariance between disturbance and regressor is no longer valid in this model. So, this gives not only biased estimate, the estimate over here is both biased and inconsistent. That means, in the limit we have this beta hat, the estimate. In the limit, as we increase the sample size, we call it probability limit. So, in the limit, this beta hat will not be equal to beta, but it will be equal to beta into sigma square x star divided by sigma square x star plus sigma square w. So, that tells us that not only is expectation beta hat not equal to beta, not only is expectation beta hat not equal to beta, even for large samples, the probability limit of beta hat, that is for a large sample, this beta hat does not converge to beta, it is beta times something. So, that is a rather serious problem, and therefore, this has to be properly tackled when the researcher is obtaining data. Error in measurement of the regressor is to be avoided at all costs. Now, we will take a look at two more things. One, incorrect way this UI enters the model, another when the UI is not a normally distributed variable. Viewers, we are now in the last lap of this module, and we will take a look at two more types. One is, if the disturbance term enters the model in an erroneous way. So, that is incorrectly specified random disturbance. So, supposing the correct model is yi equal to beta xi, or the correct representation is yi equal to beta xi plus ui, sorry, not plus ui, beta xi times ui, whereas the incorrectly specified model is alpha xi plus ui. That is, actually the disturbance term is a multiplicative term, whereas we are using it additively. Now, please see that this is not a linear model, it is not linear in parameters. So, to linearize this, what we take is the logarithm of this. In that case, it will be log of ui, log of y, and here you will have log of ui plus log of this. So, that log of ui, if log of ui, which then happens to be the disturbance term, if that is normal, if the logarithm of ui is a normally distributed variable, then statistical results tell us that ui, which is the incorrectly entering disturbance term, ui will follow a log normal distribution with mean exponential sigma square by 2 and variance given by exponential sigma square within brackets again exponential sigma square minus 1. I repeat, actually the relation is such that ui is multiplicative in nature, the disturbance term. That means we have to take the log of this and make it linear. In that case, log of ui will be the relevant correct disturbance term. If we say that log of ui is normal, then in the incorrectly specified model, which is y equal to alpha xi plus ui, where this is additive, here this ui then will follow a log normal with this mean and this variance. Now, this is a model without intercept. So, in this model, we do not take yi and xi in deviation form. Simple alpha hat is equal to yi xi divide xi square, not in deviation form. And what is yi? Yi is beta xi times ui. So, that is multiplied with xi. So, we have beta summation xi square ui, and if we take expectation, then expectation of ui is exponential sigma square by 2. So, that is like a constant, and this xi square and this xi square get cancelled. So, alpha hat is equal to beta summation xi square ui divide summation xi square. So, therefore, it means that expectation of alpha hat is equal to beta exponential sigma square by 2. When we take exponential, then this expectation of ui is exponential sigma square by 2. So, that is a constant, this x square and this x square summation get cancelled. So, that is the problem, it becomes a biased estimate once again. And finally, we come to the issue where the disturbance term enters the model correctly, but it is non-normal. One way is to go for a large sample. So, as the sample size increases, we can make use of the standard statistical result, that is, for large samples the distribution tends towards a normal distribution, or we can go for Jacques-Bera test or Anderson-Darling test to detect whether the distribution u is actually normal or not. So, that in a broad framework, dear viewers, was a discussion of specification errors and some tests of specification errors. Please go through the textbook as also the study material and do come back with whatever clarifications you require. Thank you so much for being with us in this MOOC course on econometrics. Thank you.